lectures. So good afternoon, I'm Dr. Richardson. This is lecture 3 of the course Using Vector Calculus to Solve Problems in Electricity and Magnetism. My email address is attached here. A couple of things that I've said before in lectures 1 and 2. Learning is not a passive activity. You will not get anything out of this course by sitting back and watching me write notes on whiteboard. So you have to actively take notes. This way you can follow the steps as we go through the lecture and also review the lectures afterwards. These lectures are going to be videotaped. So they're going to be available on the Google Drive link. In fact, the video clip for lecture 1 has already been posted, and subsequent lectures will be videotaped and available for you to review. Problem sets are given in this course on a weekly basis. You're meant to do them independently without consulting any other books or online resources. The whole purpose of this is for you to learn how to do a problem independently, but not sitting down and consulting a book or reference or your neighbor. And again, it's okay to do a problem and get stuck, because when you get the problem set solutions, you'll be able to see where you got stuck. In fact, when you get the problem set solutions, simply do not read them first. Make a good faith effort to do all the problems and then check the problems that you've done. Problems that you're stuck on, look at the problem set and see if you can just get hints on how to proceed by just covering the solution with a piece of paper and scrolling down. Problem set 1 and problem set 2 have been posted on the Google Drive. Early next week, problem set 1, the solution key, and problem set 2, the solution key, will be posted on Google Drive, as well as problem set 3, the new problem set 3, it will be posted early next week on Google Drive. You need to bring or purchase a ruler. It helps in writing notes and solving problems. And again, you should ask questions. So we're scheduled to go from 2 to 3:30 today in terms of the lecture. From 3:30 to 5, the course turns into a recitation section, which means that I'll be available to ask in real time, to answer in real time questions you have on problem sets, lecture material, etc. You can also send me an email message at my email address, srichards22@comcast.net, for any questions that you may have. And that's true for both during the week and the weekends, and I'll try to respond in real time. Well, I will respond to you within 24 hours of the email message. So take advantage of these resources and these strategies for learning the material. Because again, you have to take an active role in this. Okay, so where we were last time, we were talking about how to use coordinate systems in vector calculus. And it turns out that this is extremely helpful and useful because we're going to solve problems that have symmetry. So for example, if you look at a problem in 2 dimensions in the plane, there are cases where plane polar coordinates, which we previously discussed, are the appropriate coordinates to solve that problem. And so in fact, we showed that the differential surface element in plane polar coordinates is just rho d phi. I'll say this again, I mentioned this last time. There are some courses or textbooks that instead of using rho, the authors use r for plane polar coordinates. And then there are some authors, instead of using phi, they use theta. And that's perfectly fine. It's just that you have to figure out what side of the street you're walking down. So we're going to choose this scheme. Okay, in problem set 3, which you will see early next week, you'll have lots of practice with doing problems that exploit plane polar coordinates. So this differential surface element, which we derived last time, if you're shaky on its derivation, go back and look at it in the notes. It's going to be essential. The next set of coordinate systems we looked at, so this is all a review, arise when we have a problem where the system has cylindrical symmetry. So in that case, cylindrical polar coordinates, that's the way to go. So we all know what a cylinder looks like. So in cylindrical polar coordinates, you still have that angle phi that you had from plane polar coordinates. That vector has magnitude rho. Again, I need my x, y, z coordinates. And I need my unit vectors to tell the audience what my orientations are. So we discussed last lecture that one of the most useful things in cylindrical polar coordinates is to recognize that there's a differential volume element. dV, and in cylindrical polar coordinates, it's rho, d rho, d phi, dz. So a couple things about this expression. Does it make sense dimensionally? Yes. The left-hand side is clearly a volume. The right-hand side has a length, rho, a differential length, d rho. D phi is dimensionless. Angles are in radians, they have no dimensions, and dz is just a length. So length squared does give you a volume. So again, we derived this expression rigorously. If you're shaky on its foundation or where it comes from or its origin, please go back and review lecture 2. And again, one of the key purposes of problem set 3 is to give you lots of practice in using this expression by looking at cylindrical polar coordinates. One of the things you should note is that this course is relatively self-contained. There's no textbook. So everything that you need for the course will either be in the lectures or the problem sets. And in that regard, problem set 3 is very instructive because it gives you lots of review on and opportunities to apply what you know about plane polar coordinates and cylindrical polar coordinates. Okay, so we started talking about this last time, and I want to pick up from there. There are cases where you deal with problems that have spherical symmetry. And in those instances, it makes your life much easier to solve the problem in spherical polar coordinates. So again, attempt to draw a sphere. Now we'll orientate it as such. So again, my unit vectors, they're ubiquitous, but it's nice to remind the audience that they're there. So the issue in spherical polar coordinates is you're going to define a position vector, r. We showed in the first 2 lectures exactly what this is. It's I hat times the sine of theta. Well, let me define these angles first before we actually start writing. So using plane polar coordinates, this is the same angle in the XY plane, phi. And this angle from the z-axis to r is theta. Now we're in a position to write down an expression for the position vector in spherical polar coordinates. R equals I hat sine theta times cosine phi plus j hat sine theta times sine phi plus k hat cosine theta. And again, you need to make sure you understand where this expression comes from and that you believe it. And one way to check to see if you believe this thing is to see what happens in a limiting case. So for example, we're going to use this trick all throughout the course. When you get complicated expressions, make sure that they reduce to something that you know and you're familiar with. And that gives you a check on your result. Doesn't prove your result, but it just suggests that it's okay. And the more complicated the result is, if you get back to something you know, that gives you more faith that in fact you're doing the right thing. So what am I talking about? If you set the angle theta equal to 0, then the first two terms disappear and you're just left with the position vector being a vector in the k-hat direction, which makes perfect sense. Okay. So we in fact went through in great detail the derivation of this. And it's something you should be able to write down instantly. R equals I hat, it's sine, cosine, sine, sine, cosine, and it's theta, phi, and theta. And again, another way to check this thing is to prove to yourself that in fact, the magnitude of the position vector, so we are missing something. So this is not completely right. Let's clean this up a bit. And so for the student with the sharp eye, I'm missing, this is a position vector. So I'm missing the magnitude of the vector. Okay. If I didn't have the r's there, then that would be a unit vector. So one of the things you should prove is that if you take this position vector and dot it into itself and take the square root, you in fact get r. So that's another nice example of a limiting case. Now, I want to pick up really where we left off last time. We know what the differential volume element in cylindrical polar coordinates is. We don't know, or maybe we discussed very quickly, the differential volume element for spherical polar coordinates. So this is the differential volume element in spherical polar coordinates. And I'm not going to attempt to prove this in lecture for a number of reasons. I'm not that great an artist, but there's a beautiful illustration or proof of this attached to problem set 2. So compare problem set 2. But I do want to show you that in fact this is correct. So again, one thing you should do before you get started is make sure that the dimensions are right. The left-hand side is differential volume element, but it's still a volume. R squared has units of length squared. dr has units of L. Phi and theta are measured in radians. They're dimensionless. So L squared times L does give you a volume, L cubed. So how do I know that this is correct? Well, one way to know that this is correct is to in fact take this guy. So what you're doing is you're taking space and you're dividing it up into little portions dv, and you're integrating over some volume. And if this problem is a sphere, for example, you know what the answer should be. It's 4/3 pi times the radius of the sphere cubed. So does this in fact get you there? So you have to do this integral, which again is a three-dimensional integral. That's what the V stands for. So in fact, you can break this integral up into three separate integrals. All these variables are independent of each other. So the problem of doing an integral in a three-dimensional integral simply reduces to the problem of doing three one-dimensional integrals. The radius of the sphere, for example, would go from 0 to r. The polar angle of the sphere only goes from 0 to pi, not 0 to 2 pi. So check that, make sure you believe that. And finally, the azimuthal angle goes from 0 to pi. So you're in a position to do these integrals. I'll write out the integrand in any order you want. You could do the integral, the radial integral first. You could do the integral over the azimuthal angle, and then finally the polar angle, or in any order that you wish. You should show, we did this last time, that this is 4/3 pi r cubed. So that gives credence to our belief or the fact that this is the right expression for the differential volume element in spherical polar coordinates. Okay. And again, this guy appears so many times that it's something you just have to get used to being able to write down. So look at problem set 2 to see how this makes sense geometrically. And then once you have that on your belt, run with it. And again, you can check this thing dimensionally. You have to have an r squared, not an r here. And you have to have a sine theta d theta. If you put in the wrong expression for dv here, let's say you put cosine theta here, you would not get 4/3 pi r cubed. But again, this expression is going to appear so many times in applications in vector calculus that you're going to be able to just sit down and write it by heart. Okay, a couple other examples I want to look at in spherical polar coordinates. It's going to be useful to worry about spherical shells. So I know what the volume of a sphere is, but let me look at the problem of a spherical shell. So a spherical shell is just defined by an object that has a certain radius r. Okay, there's nothing inside. For distances less than r, there's nothing. And for distances greater than r, there's nothing. There's just a surface or a boundary r. So the question I would like to ask is, what is the surface? Or really surface area S for the spherical shell. So the answer is, what I need to do is take little pieces of the shell, differential surface elements ds, and just add them up over the entire surface. That's what integration is. Okay. So for example, put this in red. That red area is a differential surface element. Now, what is it? And again, in problem set 2, actually problem set 3, you will have ample practice of seeing this again geometrically, but just think about it for a moment. We just came up with an expression for the differential volume element in spherical polar coordinates, and we said it was this. Well, this can't be right for ds. the angle over phi, remember phi again is my azimuthal angle. This d phi, that's probably right. Theta is my polar angle. Sine theta d theta, that's probably okay. D theta, or r squared d theta, here's the problem. For shell, r is not variable, it's a constant. So rather than having ds look like that, the differential volume element, which is not, all I need to do is keep that r, but recognize it's a constant. And so the assumption is that that is the differential surface element of a spherical shell over the surface of the shell. Now all I have to do is do this integral. Well, r is a constant, comes out. Area is two-dimensional, so I have two integrals to integrate over. I have to integrate over the polar angle, theta, and I have to integrate over the azimuthal angle to from 0 to 2 pi. Integrating over the polar angle, I go from 0 to pi. And all I have to do is do what's in front of me. Theta and phi are independent variables, so I could do this integral in any order I want. I could do the integration over theta first and then phi, or I could do the integration over phi first or then theta. Either way, you should convince yourself that this is exactly what you think it should be. It's 4 pi r squared. One way to see that from d theta, you get a 2 pi contribution. That's easy. Sine theta d theta is a simple integral that just gives you 2. Okay. So in fact, for a shell, the differential surface area is simply r squared sine theta d phi, where r is the radius of the shell as a constant. Okay. So there's one other thing I want to do before we leave our discussion of spherical polar coordinates. I want to look at another way to find the volume of a sphere. So again, let's remind ourselves what a sphere is. It's an object that looks like that. And let me just say in words what I'm going to do. If I want to figure out the volume of this guy, another neat way of doing this is to simply divide or break up my sphere into spherical shells. Spherical shell will have a radius r, and it will have a thickness dr. So this is dr. So the question is, what is the differential volume of my spherical shell? Well, we got this halfway resolved in the previous slide. I know the area of my shell is just 4 pi r squared. To get a volume, I just multiply it by the differential length, dr. So again, what's on the left-hand side is a volume. It's L cubed. Here's a length squared, and here's a length. So dimensional analysis is a trick that we will always use. So that just tells me what the volume of this shaded region is. The volume of a shell. That's not the volume of the sphere. So calculus comes to my rescue. If I want to find the volume of the sphere, all I have to do is add up the volume of this shell over the entire sphere. And that means I have to go from R equals 0 to R equals big R, where big R is going to be the radius of my sphere. So suppose my actual sphere is indicated by that dotted line, and what's in red is just a spherical shell. And if I want to figure out what the volume is of this entire object, this entire sphere bounded by this dotted line, I break the problem up into spherical shells highlighted with red hatches, and then just add all these guys up from 0 to R. 0 to big R. I know what the differential volume element of the shell is. It's just 4 pi R squared dr. And we all know how to do this integral. And lo and behold, it gives us what we expect to get. Gives us the volume of the sphere. So this is another way of getting the same answer, but this idea of introducing breaking the problem up into spherical shells and then just summing up the volume of each one of those shells, that's a problem we're going to use a lot in electrostatics later. So it's useful to highlight it and talk about it now. Okay, so that's it for coordinate systems, and in a way that's sort of the end of the review from last time. So, and again, I don't mind going over this again, but I'll go through it very quickly. So one of the things that you're going to do in problem set 2, if you haven't done it already, is recognize that you need to recall lots of things from your early calculus course about integration. So what is integration in terms of words? So suppose you have a function of a single variable, f of x, and let's say you have a point A and a point B, and you want to find the area under the curve, the area under this function from x equals A to x equals B. So one way to do this, to a good approximation, is simply break the area up into rectangles. So let's say 2. So the area under this curve, let's call that A. The area under this curve is just the volume or the area of one rectangle times the area of another rectangle. It's not exactly, but it's roughly. So the area of one rectangle is just delta x sub 1, let's say, 1 for the first rectangle. So width of the rectangle times the height. And the height is just the value of the function at x1. So this is the length times the length that gives you an area. So that's just the area of rectangle 1. What about rectangle 2? Same story. It has a width, delta x2, and it has a height that's equal to the value of the function at x sub 2, which is some point along the x-axis. Now again, this is an approximation Because if you look at this curve, you look at this diagram, just cutting this up into two triangles is not going to capture the entire area under this curve from x equals a to x equals b. There is some missing information in blue. So all that's missing. So that's why that's an approximation. But calculus comes to your rescue. If you want to find out exactly what that area is, then you simply divide the region under the curve not into two triangles, but two rectangles, but many rectangles with delta x of I, for which you can evaluate the function at that value x of I. And you don't take 1 or 2 or 3, you take a large number, n, some finite number, and then you take the limit of that expression as n goes to infinity. And that is exactly what we mean by an integral. That is an integral. That's exactly what you are doing when you do an integral. So this is very powerful. You know how to do integrals by techniques that you learned as a youth. But these techniques involve really summing up creatures like this from 1 to n, and then taking the limit as n goes to infinity. Now, nobody actually does that when you do take an integral. Its trick is that these techniques encompass all of that, so they make your life a lot easier. So what are these techniques? And again, this is a quick review. There are lots of ways to do integrals analytically as well as numerically. We are not going to talk about doing integrals numerically, but it's a very important topic. There are lots of programs out there that can do these things, but I just highlight a few useful tools. And again, we gave examples of this last time, so I'm not going to do that. So you can solve an integral by substitution, and we actually gave an example, and you have tons of practice with this method in problem set 2. So I advise you to master those problems. Second useful way of doing integrals of functions of a single variable is the celebrated integration by parts. Again, we looked at an example last time, and I've given you some more practice problems to worry about how to do that in problem set 2. Third technique, which turns out to be extremely useful, and I was not shy. I may have gone overboard a bit in problem set 2, but it's important because if we tackle these integrals now, then we don't have to worry about them when we're trying to solve problems like calculating electric fields or electric potentials or using Gauss's law. And so this technique involves trigonometric substitution. And again, problem set 2 is the way to review those techniques and master them. So just for completeness sake, I did not last time go into any detail on this fourth method, and I'll just give a quick example of it now. This is so-called method of partial fractions. And it turns out it's going to be useful. So all we're doing is building up mathematical tools now. We get all this machinery out of the way. These are mathematical calisthenics that we're performing, and we will use these guys, definitely. So for example, here is an integral that you may want to solve. And the previous 3 methods, integration by parts, integration by substitution, or integration by trigonometric substitution, may not work. So the trick is to divide this integral, or break it up into 2 parts. Because in this example, you immediately realize that 1 plus x times 1 minus x gives you 1 minus x squared. And the problem now is you divide the problem up into partial fractions, 2 fractions. And the question now is, what are C1 and C2? So for all of this to work, C1 over 1 plus x plus C2 over 1 minus x, it's got to be equivalent to 1 over 1 minus x squared. Because after all, 1 plus x times 1 minus x is 1 minus x squared. So you want to find C1 and C2, you need 2 equations to solve for those 2 unknowns. So algebraically, this expression tells me that C1 times 1 minus x plus C2 times 1 plus x has to be equal to 1. I can simplify this expression to get C2 minus C1 times x plus C1 plus C2 equals 1. So the only way this expression is going to be valid is that this guy, C2 minus C1, has to vanish. There is no term involving x on the right-hand side of this equation. So C1 plus C2, or let's do what we just said. C2 minus C1 has to vanish. That's one equation, 2 unknowns. And then C1 plus C2 has to equal 1. So you can solve these 2 equations very easily, and you'll discover that C2 and C1 have to be identical, and they have to equal 1. So what you have done is taken an integral that's complicated, that you really can't do by the other 3 methods, and you divided it up, or you've broken it up into simpler integrals that one of the 3 methods, 3 previous methods will work. And I'll tell you the answer, and you should check it. It's just the sum of 2 natural logs. And again, we're doing indefinite integrals here, so we're not worried about the limits of integration. We will obviously have to worry about them when we solve an actual problem. Okay, so what I want to do next is face the problem that integrals are nice. You have lots of practice problems with them in problem set 2, but integrals, at least the integrals we have looked at so far, don't involve vectors. Well, there are going to be integrals that do involve vectors, and we're going to have to figure out how to deal with them. So my philosophy is, let's get the mathematical expertise out of the way first. Let's learn the math first, and then we'll worry about applying it later. Excuse me. So what am I talking about? So the first type of integral that involves a vector is something called a line integral. And you may see this referred to in other books or by other people as a path integral, for reasons that'll be clear in a minute. So a couple of ways to write this guy. So let me write it this way. So A is a vector, and D is my displacement vector that I introduced way back in lecture 1. And A is just some vector. Now this C under the integral stands for contour or circulation or path. So that's your signal that you're dealing with a very special type of integral, something called a line integral or path integral. I think I'll refer to them as line integrals. So I need to take a vector A, dot it into displacement dr, And then I need to evaluate this integral over some contour, circulation, or path. So it behooves me to point out that this is not the only way that you'll see line integrals or path integrals in the literature. Some people use DL for DR, and in this case, it's a differential line element. It's the same thing. I'm just going to use the convention here in discussing line integrals in this course. And finally, there's a third convention that people will use. Some people use lowercase s d sub s as a differential line element. All three of these are equivalent ways of doing or writing down a line integral. So from my point of view, from our point of view, the only way to see how this works is to pick an example. So let's do that. So if you're going to do a line integral, you need a couple of things. First thing you're going to do, so this is an application. Of evaluating a line integral. So the first thing you have to do is be given a vector. Because after all, in that integrand, there's a vector. So let's pick an example where the vector is y squared I hat plus 2x times y plus 1 j hat. So I'm picking a vector in plane polar coordinates. I'm sorry, I'm picking a vector in Cartesian coordinates, two-dimensional Cartesian coordinates. So the next thing I need to do is tell you what C is. What is the path? I can't do a line integral until you tell me the path over which I am evaluating the integral. So I'm going to do a problem where I will have many paths. And I will do this problem systematically. So here's a point A, and here's a point B. So there will be a path, which I'll call sub lowercase path I, and path 2I. So it has two parts. And this point I'm going to call 1 on the x-axis. This point I'm going to call 2. This point let me clean this up a bit first. I'm going to call y equals 1. And this point here, now you see the necessity for a ruler, not just doing line integrals, but lots of applications, y equals 2. So again, this point I called A, and this is a point B. And I will call this guy path 2. So I have two paths in this problem. Path 1, that's just going to be I plus double I. So that's going from x equals 1 and y equals 1 to x equals 2, y equals 1, plus going from this point, x equals 2, y equals 1, to this point where x and y are both 2. That's path 1. Path 2 involves going straight from from the vector B to the vector A. Remember, vectors are points. So I need to evaluate this. That's the line integral. And I'm going to do it first over path 2, or C sub 2. So if someone gives you a path integral, then she has to tell you what the path is. Otherwise, you can't do it. So there it is. So I'm going to do this part first, and then I'll do path 1 second. Okay? So path integrals, line integrals involve doing integrals over paths. Okay, so how do we do this? We need to evaluate v dot dr over a path. And again, I don't mind rewriting this figure because it's going to tell me what to do. If I don't have this figure, I'm not going to know what to do. So path 2 involves going from A to B, where x equals 1 here, y equals 1 there, and x equals 2 here. And let's put this in and we'll bring it back in a minute. And this point is y equals 2. Okay, and so this is path 2. Okay, so I know the path. So let's tackle this integral. So there are 3 things you have to be able to do. You need to know the vector over which you're doing the line integral. You need to know what the differential line element is, or the displacement vector is, dr, and you're going to need the path. So first things first, remember we defined this problem so that v was y squared I hat plus 2x y plus 1 j hat. So what is dr? Well, that's easy. That's just a displacement vector in 2 dimensions, 2-dimensional Cartesian system. So I hat dx plus j hat dy. So I'm going to need to evaluate what's inside this integrand. That just means all I have to do is take the dot product of v with dr. And I know how to do that. I know how to take dot products of vectors. So that's y squared dx plus 2xy plus 2x dy. So you may ask, well, what have you done? Well, I've done something very critically important. I've taken an expression that had 2 vectors inside of it, and this integral had 2 vectors, and I have reduced it to scalars, numbers. Why? Because doing integration over numbers is far easier than doing integration over vectors. Okay? So I have the solution to 1 and 2 right here. So the remaining task is to evaluate this expression over this path. So I'm going to do something smart, I think. I'm going to keep the picture of my path there. And the rest of this so remember this is, sorry, this is x equals 1, this is x equals 2, and I'll rewrite this result up here. So we've discovered that V dotted into dr is simply y squared dx plus 2xy plus 2x, the entire quantity multiplied by dy. So what I need to do is evaluate this expression over C2. So this expression just involves, for this particular example, structure that looks like that. Now, this looks like a mess because it involves two variables, x and y. And I'm claiming that when I do a line integral, I'm really doing it along a path. So it's really a one-dimensional creature. So I have to make a choice here. I can either do my integral over x or I can do it over y. I can't do both. So I am going to do the problem by integrating over y. Because if you look at the diagram, if you go from point A to B and you change y, y just goes from 1 to 2. Now, I still can't do this integral because it involves x and y. So I need to write this entire integral in terms of y. And there's a very easy way to do that. Path 2 along path 2, what you have is the equation of a line. Y equals x, slope 1. That's the way I set the problem up. This also means that dy is the same as dx. So my line integral over path 2 is just the integral over y from 1 to 2 of y. So I'm going to do this one term at a time. Got 3 terms. So I have a y squared dx, but dx is the same as dy. So that's term number 1, can't knock down. Term number 2 is 2xy dy. X is the same as y. So this is 2y squared dy. And my third and final term is going to be 2x dy, but x equals y. So that's just 2y dy. And now I am in perfect shape to do this integral. This is a simple elementary integral to do. Okay? There is only one variable of integration, y. The limits of integration are given. So I'll leave it to you to verify this. This equals 10. Okay. So what I've done is evaluate the line integral over the path of C sub 2 from A to B. And it equals a number, 10. Okay. Now, I'm not finished because there were 2 other paths that I wanted you to evaluate this in. Actually, one other path that we wanted to evaluate this line integral over. So again, let's go back to the diagram. So let me just stop for a minute, catch my breath. Okay. So let's go back and look at that diagram. Sorry. Look at that version. In order to do a path integral, you're going to need to know what the path is. So you're going to have to draw a picture. Pictures tell you what to do. So in fact, C1 or path 2, path 1, has two parts to it. One I called I and one I called double I. This is x equals 1. This is x equals 2. This is y equals 1. And this is y equals 2. And again, you know, it's helpful. Let's put in our unit vectors. Okay. So let's save ourselves some work. I already know what v dot dr is. It never changes. It's simply x squared. In this problem, it's y squared dx plus dxy dy plus dx dy. That's all it is. And so that's the easy part. What I have to do now is evaluate this line integral over C1. And there are two parts. One is over the path I, and one is over the path number 1, path I and double I. I sort of broke it up into two parts. And there's a second part to this line integral. I'm just going to do the first one here, and I'll come back to the second one in a minute. Okay, so how do I evaluate this guy? Well, again, look at the figure. It's sloppy. The figure is going to tell you what to do. So along I, starting from x equals 1, y equals 1, to x equals 2, y equals 1, I notice that along I, so along I, y is 1, but that's a constant. So dy is 0. So if dy is 0, then I'm only going to get a contribution in this problem for the first term. This guy is going to vanish because it has a dy, and this guy is going to vanish because it has a dy. So what was complicated along path part I just reduces to this. Y again is just 1. So this line integral is easy to evaluate. It's just the integral of dx from x equals 1 to x equals 2, and that's just 1. Okay. So the answer for your line integral depends upon the path over which you do the problem. Now, I need to evaluate. So I've gone from here to here. Now I need to go from here to here. Well, an easy way to do this is not to throw everything out the window, but just some of these things. Let's keep our figure here. Actually, we could have kept that guy. So now I'm doing this along. I'm evaluating the second guy. Same story. V dot dr never changes. There it is for this particular problem. But I just have to evaluate it. Along the path from here to here. So let's set this up along that path. X is a constant, it's 2. So that means that dx, by definition, has to vanish. Y is the only thing that's changing. Y goes from y equals 1 to y equals 2. So what does that mean for what's going on here? In this case, dx is 0, so that first term disappears. Y is 1, x is a y is going to be a variable. So let's look at the second term. The second term is going to involve 2 times x. X is a constant, and y is a variable. So that's this guy. And the second term is going to involve 2x dy. X again is a constant. 2 times 2 is 4 dy. And so this is the integral I need to evaluate, where y starts from 1 and it goes to 2. So I've reduced the problem to a simple integral over a single variable. I leave it to you to evaluate this. It's an elementary integral, and it's in fact 10. Okay, there's one more path integral that we're going to do, or line integral we're going to do. And I am actually going to suggest what it is, outline it, but I'm leaving it up to you to in fact prove. So again, I need to go back to my figure. I don't have any problems. Let's draw it again. So no problem with rewriting this. Here's x, here's y. And remember in this problem, I had 2 points, A and B. And originally I looked at the path 2 as going from A to B. Now I'm going to reverse that. And worry about the path from B to A. So I want you to evaluate this line integral of v dot dr over this path C. It's a different path. So I will set this up for you, and I'll leave it up to you to do it. So here is a very important suggestion. The differential line element is always going to be, in this case, for two-dimensional Cartesian coordinates, I hat dx plus j hat dy. Don't get hung up into trying to figure out, well, you know, really dr points in this direction and therefore the x component is a minus. No, don't do that. Let the problem come to you by just solving it and worrying about that issue when you evaluate the limits of integration. So again, let me remind you, in this problem, v was y squared I hat plus 2x y plus 1 j hat. So again, v dot dr, that's easy to evaluate. That's y squared dx because of the dot product properties of the unit vectors. And then I get a 2xy plus 2x, all of that times dy. So I'll give you some structure. I'll give you some hints on how to start this problem. First of all, along C, I have a line whose slope is 1. So x equals y. dy is just dx. So neither x nor y are constants anymore. And the task now is to take this expression and write it either in terms of x or y. You have a choice. You could do it one way or another. And I suggest you do it both ways because you should get the same answer. Now, the final hint, I'll leave everything to you. So again, this is x equals 1. This is x equals 2. This point is y equals 1. And this point is y equals 2. Let's say you do the integral over x. Then x is going to start at the point 2 and it's going to end at the point 1. That's where this change of sign comes into play. So you don't have to worry about changing anything here. You don't do anything with this differential line element. You leave it the same, even though the path here is minus or opposite the path in the earlier example. Everything will work out if you do your limits of integration correctly. Namely, to go from B to A, you have to start with x equals 2 and end up with x equals 1, not the other way around. And I maintain that you should evaluate this yourself, this line integral over C, and you will find that in fact, well, you see what you find. I won't tell you. And try it. Figure out what this is, and try it two ways. Try the integral over x or the integral over y. Okay. So I've given you at least 2 additional practice problems to do. There are lots more in problem set 2. And the only way to master calculating line integrals or path integrals is by, in fact, doing them. The next type of integral we want to do that involves vectors is something called a surface integral. Why we want to do these things and evaluate them, I'm going to leave that to another day. Okay, so I just want to jump in and do the problem. So I need to give you a surface. So I'm going to pick a surface that's very nice, that has nice high symmetry, so that the integrals are easy to do. And again, my ruler comes in very handy. So I am in 3-dimensional Cartesian coordinates. And I'm going to look at a surface, and my surface will be a box. So my box typically has 6 sides, but in this problem, I'm going to just worry about 5 sides. So let me number these things first, and I'll explain what these numbers are in a minute. So surface 1 is going to correspond to the front of the cube or box. I guess probably cube is a better term than box. Surface 2 is the back of the box. Surface 3 is the right-hand side of the box or cube. Let me just solve that problem right now. Cube. Surface 4 is going to be the left-hand side of the cube. And I'm only going to worry about the 5 sides, not the 6 for this problem. Surface 6 will be the top. So what I want to do here is calculate this creature. And again, I use the same symbol V, but it's going to be a different vector. And this is an example of a surface integral. How do I know that? Well, this large S under the integral tells me, it alerts the reader that, wake up, this is a surface you're integrating over, not a curve or path. Okay. And I'm going to do this problem in 5 parts. I'm going to integrate over surface 1, and then I'm going to do the surface integral over surface 2, and I'm going to add up, and I'll get 5 contributions. So this is a problem that breaks up into 5 parts. So let's get started. The only way to see what a surface integral is in fact do an example with it. So let us evaluate the surface integral of V dotted into ds over surface 1, where surface 1 is clearly there. So what's missing? Well, lots of things. First of all, I need to tell you what the vector V is. I need to tell you what the differential surface element, nice word, but we've seen this creature before. I need to tell you what that is. And then finally, I need to tell you what the surface is. So let's pick a problem where I do all of this. V is going to be a vector that's 2xz I hat plus x plus 2 j hat plus y times z squared minus 3 k hat. So that is my vector. So that's 1 down, 2 to go. Now I have to figure out what is the differential surface element, ds, over S1. I'm only going to get that information by looking at my figure. So 2 things I need to know. I need to know the unit normal vector, and I need to know the magnitude of ds for surface 1. So for surface 1, the unit normal vector is always going to point outside, away from the closed surface. So n hat is going to be simply the unit vector I hat. So what is ds? Well, ds is just going to be this red shaded region. So if you look at the diagram, that's a surface, but you could break it up into small surface elements. That's an area, and they have to have each an area of dy times dz. So if this is key to see this, if you're having problems seeing this, I refer you to problem set 3. So I go into great detail, some useful exercises where you can practice evaluating the differential surface elements in a number of coordinate systems. But here, this red hatched area is obtained by just integrating small differential surface elements that look exactly like that. Now we're good to go, because all we have to do is take the dot product of V with ds, and that's easy in this problem because ds only has one contribution due to I hat. If you dot I hat into, if you dot ds into V, you only get one simple expression. You get 2xz dy dz. Okay, so now all you have to do is the last step. So we've done one, we've identified the vector inside the surface integral. We've done step 2, we've identified the differential surface element. Now step 3 is to take this creature and do the integral over S1. So let's do exactly that. So v dot ds is 2xz dy dz. So I don't need this anymore. And again, this is only for one surface, S1. So the integral over S1 of v dot ds, again, it's a two-dimensional integral. 2xz dy dz. But I can make things a little easier when I go back to my diagram and recognize that this cube is a very special cube. It's a cube that has a corner at the point 0, 0, 0, and it intersects the x-axis at x equals 2, the y-axis at y equals 2, and the z-axis at z equals 2. So that means that along S1, x has got to be equal to 2. So this is 4z dy dz. And you're almost home. You've got a problem involving two integrals over two variables, z and y, but they're independent. Excuse me. So this breaks down to integrating z from 0 to 2, z dz, times the integral of dy from 0 to 2. And you can evaluate this elementary integral. He is 16. Okay, so I've done 1/5 of the problem. What I like to do in the remaining 7 or 8 minutes is do other parts. So that's just the integral due to surface 1. And again, please check that. So how about surface 2? Well, surface 2 is going to be the back of the cube. And I leave it to you to prove to yourself that the differential surface element for S2 is minus I hat dy dz, because the unit normal vector and hat is going to point in the minus I hat direction. V, again, doesn't change. It was what I was given the problem to solve. It's 2xz I hat plus x plus 2j hat plus y times z hat, y times z squared rather, minus 3 k hat. To evaluate the surface integral over surface 2, I have to take the dot product of v with the differential surface element along surface 1. I look at these two vectors, I take their dot product, and I realize that things simplify. This simply reduces to minus 2xz dy dz. So this is the guy I need to evaluate over surface 2, minus 2xz dy dz. And now I realize something interesting. Even though this looks complicated, I mean, this looks like a mess, I'm doing this integral over S2. Over S2, so over surface 2, x by definition is 0. It's the back of the cube. So since x is in the integrand, that surface integral vanishes because x is 0. So 2 down, 3 to go. Again, let's get rid of everything that's, actually let's get rid of everything. And I don't have problems in redrawing the picture. So I'm working in Cartesian coordinates, 3-dimensional Cartesian coordinates. I have a cube. This is not drawing the scale. But it's an artist's rendition. It's not even drawing the scale at all. So let's do it differently. Let's start with the axes first. Okay, and that's going to make life easier. So here is one side. My cube. Another side of my cube. Okay, this is the x-axis, the y-axis, the z-axis. That's the origin, 0, 0, 0. This is x equals 2. This point is y equals 2. And this point is z equals 2. So the third surface I needed to look at, I call S sub 3. So let me go back and figure out what my convention was. Okay. So S sub 3, I defined to be the right-hand side of my cube. So that means the unit normal vector is going to look like that. So I need a couple of things. First thing I'm going to need to write down is the differential surface element over S sub 3. You can write that down by inspection. That's simply j hat, positive j hat dx dz. The vector doesn't change, still the same. 2xz I hat plus x plus 2 j hat plus y times z squared minus 3 k hat. So, we're starting to get used to this. In order to evaluate that surface integral, I need to evaluate this integrand. I need to take the dot product of these guys, this vector with this. The only one that survives due to the property of unit vectors and scalar multiplication is the j hat term. So this is going to reduce to x plus 2 dx dz. So the surface integral over S3 is just going to be this creature, which is x dx dz has two terms plus 2 dx dz. There are two parts to do. Okay, so to go further, you need to look at the diagram. You need to look at the picture. Surface 3, which is here, is defined by setting y equal to 2. That's exactly what you mean by surface 2. It intersects the y-axis at the point 2. So that means that dy has to be 0. And you don't have any y's or dy's in here, so you're fine. And then all you have to do is evaluate these two integrals. It has two parts to it, this one and this one. X is going to go from 0 to 2, and z is going to go from 0 to 2. So I'm going to come to a conclusion and tell you that, in fact, this is equal to 12. So you should prove that. So let me wrap up today's lecture. I'll leave this diagram here, and I leave it to you as a very useful exercise to prove to yourself that you know how to evaluate surface integrals, at least in this example. And I leave it to you to prove that, in fact, for this case, we've done 3. 2 more surfaces need to be done. You need to show that the integral over S4 is v dot ds. This was the left face. And you need to show that, in fact, that surface integral equals minus 12. And then the last surface integral that we needed to do in this case was over S sub 5. That's the top. We're not worried about the bottom of the cube in this example. And that will be equal to 4. So you need to show these are in fact true. Okay, so let me summarize. So I have reviewed, because we actually did this back in lecture 2, a discussion of spherical polar coordinates with the suggestion that you need to consult problem set 1 and 2 to see how to get the differential volume element spherical polar coordinates. Last lecture and today's lecture, I have reminded you about 4 useful techniques for integration of functions of a single variable: substitution, trigonometric substitution, integration by parts, and a method of partial fractions. Problem set 2 gives you extensive practice with this. We have introduced the idea of a line integral or path integral. Haven't really said why these things are useful, but suffice it to say they are. And in problem set 3, which will be available online on Monday, you'll have lots of practice with that. Integration, problem set 2, and spherical polar coordinates, problem set 1 and 2. And finally, we've introduced the idea of a surface integral, where I have done really 2/5 of a problem. I leave it to you to check. I gave you the answers. I need you I leave it to you to verify that. And you'll have lots of practice with surface integrals in problem set 3. Final type of integral we need to look at are volume integrals. And we will do that in lecture 4. And we also will start talking about in lecture 4. So this is next week. And next week we will start talking about vector operators, the gradient, the divergence, and the curl. So again, it is absolutely essential that you review this material in terms of vector analysis, in terms of coordinate systems, and now what we're really doing now is vector calculus. But vector calculus is built on a fundamental understanding of vector analysis as well as coordinate systems. Okay, I'll say that when we start talking about vector operators, we will define them, we'll show how to use them, and then we'll actually give some physical insight as to what these things mean. The gradient, divergence, and curl. Okay, so that's it for lecture 3. In summary, problem set 1 and problem set 2 are available on the Google Drive. The solution keys for problem set 1, problem set 2 should be available at that same location early next week. And problem set 3 will be available on that same link early next week also. Okay, so questions and comments. Hello. Folks out there, any questions, comments? So this is the time for recitation. So in principle, I'm here for, yes.
Can you hear me?
Yes,
Hello?
I can hear you. Can you hear me?
Oh, sorry. Yeah, now I can hear you.
Okay,
I couldn't find the answer sheet on Google Drive, so you think you could I have you email it to me today after
Dr.
take
Brower
it off.
Thomas, I'm going to throw that question to you.
I didn't hear the question completely.
Can you repeat the?
I couldn't find it on Google Drive.
You can't find.
I couldn't find the answer sheet on Google Drive.
Okay, I heard you can't find something on Google Drive.
No, I can't find the answer sheet, but I can email you, Dr. Brower.
Answer sheets. Okay, so let me just.
No,
okay.
Tina, let me just.
Oh, okay.
Yeah,
okay.
the solution key as of yesterday, the solution key for problem set 1 is still not posted, as well as the solution key for problem set 2. It's still not posted. So you're absolutely right. The only thing that's available in Google Drive at the moment are the actual problem sets. So as I said before, the solution key to problem set 1 and problem set 2 should be available in the drive early next week.
Oh, okay.
Okay, so that's not a mistake at your end. The solution key is not there yet. So right now you have problem set 1 and problem set 2, but you don't have any solution keys.
Okay, that's fine. Thank you.
Okay, sure. Now I can't mail them out to you because they're 55 megabytes. So there's a technical issue at my end. My internet provider is Comcast, and they have a limit of about 32 megabytes for a file attachment. So it's a technical problem on our end that should get resolved early next week. And you should be able to see the solution key to problem set 1 and problem set 2 in the drive early next week. I can't tell you exactly when, but it should be early next week.
Okay, thank you.
Thank you. Does that sound right, Tina?
Yeah.
Okay.
The azimuthal limit is 0 to pi always, or is it, or I mean 0 to 2 pi always, or there's a case when it's 0 to pi?
So let's remind it. Oops, sorry. My mistake. So the question is looking at spherical polar coordinates. So again, that's X, Y, Z. So this is spherical polar coordinates. So in spherical polar coordinates,
Okay. No.
remember, well, I mean, it's a good question, so I'm going to go through. So here's my position vector, R. So if I drop a line that's perpendicular to the XY plane, I can define another line here such that that's a right triangle. So I have two angles here. In our discussion of plane polar coordinates, I have something called the azimuthal angle. Now, this is actually a good question. Then I have another angle from the z-axis to the position vector, and that angle is theta, and that's the polar angle. So I will use the convention that the phi is the azimuthal angle and theta is the polar angle. There are some textbooks that use the reverse convention, and they call theta the azimuthal angle, and they put it down here, and they call phi the polar angle, and they put it up where we have. And I just point that out because, I mean, that's the way some people roll. So you just have to make a decision of what convention you're going to use. And that's not the convention that we're going to use here, but you'll see this. Other authors will do this. So what do these values mean? What do they do? So zero, R in principle could go from 0 to infinity. That's how you can define any point in space. in spherical polar coordinates. Theta, the polar angle, is going to start at 0, and it's not going to stop at pi over 2, because if it stopped at pi over 2, it would just hit the xy plane, and you'd get a hemisphere, not a sphere. So you want this thing to go all the way to pi. All right. Once you do that, that defines everything that you need to know about the polar angle. That doesn't give you the entire sphere, though. The entire sphere, let's do this in black, sorry. The entire sphere is going to be obtained by rotating the azimuthal angle all the way around. You start from here, and you go all the way around, 10 degrees, 30 degrees, pi over 2, 2 pi over 6, and you come back to where you started, which is 2 pi. So those are the fundamental bounds or limits of r, theta, and phi in spherical polar coordinates. And my position vector is going to be a function of all three of those variables. And so this is true for a sphere, hence it's called spherical polar coordinates. If you wanted a hemisphere, half a sphere, the way to get that is to make the polar angle only go to pi over 2. Does that address the question? So again, two things. This convention here that other people use, I mean, you'll see some people will actually put, some people, instead of putting theta here, they'll put phi here. Instead of putting phi here, they'll put theta there. That's fine, but that's not what we're doing. And obviously we have to be consistent. So this is the convention we're going to use. Okay, other questions? So again, this brings up, so the purpose of problem set 1, again, so the solution key is not yet posted, is to review vector analysis, vector algebra, dot products. You gotta learn how to crawl before you can walk. Purpose of problem set 2, if I recall, is to make sure that folks are very comfortable with techniques of integration. And actually, got a little ambitious, problem set 2 actually does have examples of line integrals in it. So again, you'll have a lot on your plate for next week when the solution keys are available. And problem set 3 will be, actually problem set 3 is going to be, I spent a lot of time on problem set 3 to make it self-contained. It's going to be a very nice review of coordinate systems, spherical polar coordinate systems, cylindrical polar coordinate systems, plane polar coordinate systems, what the volume elements are, what the differential surface elements are, what the what the displacement vectors are in all those 3 coordinate systems in nice pictures. And it will have more examples on line integrals and surface integrals. Okay. So don't attempt problem set 3 until you've mastered problem set 2. Don't attempt problem set 2 until you've mastered problem set 1. So folks who are where we are, this is the 3rd lecture, so folks should really have had problem set 1 finished and most of problem set 2, a lot of problem set 2 done. And then next week, you'll be able to go over your solutions for those 2 problem sets. And then problem set 3, once you do that, you can start looking at problem set 3. But 1 comes before 2, comes before 3. Other questions or comments? And again, I'm happy to go over the problem set. I won't tell you how to do the problem set, but if you're stuck on something, I can go look at a hint. I said something, I guess the first lecture, and I'll say it again. You know, no 2 people learn the same way. And we're in the 21st century. So there are a lot of tools out there. There's Khan Academy, which is free. If you know about it, then I'm preaching to the choir. If you know nothing about it, then just jump into it. Google it, and you'll see it's got a lot of nice online videos on lots of things. There is something else that's free called Wolfram Alpha, invented by Stephen Wolfram, who's the author of Mathematica. It's also free, and it allows you to do lots of mathematics online for relatively complicated problems. I would not suggest, I mean, the problems you have in problem set 2 of doing integration, you could, if you wanted to, ask Wolfram Alpha to do those integrals. You'd learn nothing. Okay. Other thing I want to point out, people have pointed it out to me in the past. There's something called Paul's Online Calculus Notes. If you want to review your calculus, it's free. And folks have said that they've found that useful in previous courses that I've taught. And I have to point out, especially in this age of COVID-19, OpenCourseWare at MIT, which has been around for about 25 years. Essentially, not all, but most of the courses that have been taught at MIT, from architecture to synthetic biology to chemical engineering, the lecture notes, course material, and problem sets have been posted. So there's a big difference between OpenCourseWare and Khan Academy. Khan Academy, Sal Khan really starts from the basics of various topics: thermodynamics, organic chemistry, linear algebra, differential equations, economics. You can find all that material at OpenCourseWare, the OpenCourseWare site of MIT, which again is free, but you have to hunt for it. And again, a lot of it depends upon how ambitious you are. So in principle, someone in Bangladesh could learn the fundamentals of partial differential equations by just going to the appropriate course online at MIT OpenCourseWare. So the material is there. Khan Academy is a little different in the sense that he really puts a lot of time and effort to make his lectures clear and transparent. That may or may not be true with all the lectures online and OpenCourseWare, but there's a lot of information there. And again, I don't think all the courses are there, but probably 85 or 90% are there. So if you're interested in an MBA and you want to see what Finance 1 is like at the Sloan School of MIT, the course is there and it's free. And there are probably other resources. If people find them, let me know. There is MATLAB, which is a wonderful numerical device invented to do linear algebra. It's not free. And there's Mathematica. It's not free. But typically most universities should have licenses for these two products. People probably, especially students in the engineering fields, find MATLAB to be far more useful than Mathematica. Any other free devices that people can think about or resources out there? I mean, these are the key ones that come to mind for me. I'm sorry. Well, no, this is, we just started. This is the third lecture out of 12. But the OpenCourseWare is extensive. It covers the galaxy almost. Khan is not as extensive. Wolfram Alpha is nice, but you know, there are some integrals that you can give it and it'll blow up. Paul's online calculus notes. I've not used it personally, but students have used it in the past and they like it. And also you can just YouTube. You know, you can use, so sorry. YouTube is not just for looking at music videos and, you know, local things happening. Folks who have discussed topics and they've made videos and they put it on YouTube, and it's varying quality, but, you know, you should look at it. It's there. Because we really don't know how long. I mean, there's this discussion of, will we actually get back to a world where there will be in-classroom instruction and what will it look like? And excuse me, I think we'll get back to that at some point in time, but it's going to take a while. So there's going to be a universe, this hybrid universe of online learning plus in-person learning. So again, you don't have the in-person learning in this course, but if you have questions by email, you know, I'm willing to address them and answer them within 24 hours. Any other utilities that people can think of that are helpful or have found helpful? I really do like Khan Academy though. I highly recommend it. I definitely like Wolfram Alpha. I don't know anything about Paul's online calculus notes, but people like it. And OpenCourseWare is definitely good, but there's a lot of stuff out there. So you have to be judicious in what you want. At the end of the course, I will come up with a list of textbooks in electromagnetism that I like, that I can recommend for future studies and readings. But I don't want to do that right now. I mean, this really is just meant to be a self-contained exercise, and we'll worry about textbooks at the end. Okay, other questions, comments, problems, issues? So again, you guys have done a lot of work already, and we will on our side make the solution keys available for you next week. And again, feel free to, I already found, thanks to somebody last week, there are at least 2 errors in one problem set, and I've corrected them in problem set 3. So if you go through a problem on the problem set and you see a typo or an error, please bring it up.
Okay.
Okay.
Alrighty.
So again, we can go, you know, how many people are out there now?
I think it's just the 3.
Okay. So is the third person going to stay on, or do you have any additional questions or comments?
No, he hasn't said anything.
I'm sorry.
No, that person is muted.
When you said 3, Tina, you meant all of us?
Yes, so there's Ashley, myself.
The 3 people. Okay. Right. Okay.
I'm pretty sure there are people who are registered that are going to look at the video because they're of time difference.
So, and again, the video clip for lecture 1 is available on the Google Drive. I saw it earlier in the week. It's there. The video clip for lecture 2 and 3, they should appear at the Google Drive sometime early next week also.
Yes.
Okay. I'll be heading out. Thank you, Dr. Richardson.
Okay. Thank you.
And we'll
See,
Bye-bye.
enjoy your
Bye,
holiday. Take care.
Your one. Bye.
Thank you.
Thank you. I had trouble hearing her. Okay, so I think we're done.
So will you stop the video?
Yes.
Stop recording. Okay.
Yes. Oh no, I can't. I'm sorry. You're the host, so you have to make me the host, or you have to stop it.
Okay. So let me stop it then. So we're done. Also, I should just log out.
Yeah, but it
Okay.
says it's still recording.
So
Okay.